Hello and welcome. We hear about artificial intelligence all the time, but today we're going to pull back the curtain and look at the absolute ground floor. We're going to explore the simplest AI brain there is, the feedforward neural network. Come on, let's follow a single piece of data and see how an AI really thinks.
I mean, that's the big question, right? When you ask an AI to do something, or it magically identifies your cat in a photo, what is actually going on in there? It feels like some kind of digital wizardry, but I promise you, by the end of this, we're going to have it all figured out, one simple step at a time.
So here's how we're going to crack this. We're going to follow one little piece of information on its entire journey through the network. Think of us as tour guides, and we're following a package as it moves through a really smart, really organized factory. All right, our journey starts with the bedrock of pretty much all of modern AI. It's called the feed-forward neural network, or you'll hear it called an FNN for short. This is the simple yet super powerful engine that really kicked everything off. And the most important thing to get is right there in the name. Feed forward. Information comes in one end, it travels forward through a bunch of layers, and then it pops out the other. That's it. It's a one-way street, no U-turns allowed, and definitely no looking back. And that one-way flow, that is the thing that makes an FNN what it is. It's totally different from other networks, like a recurrent neural network, or RNN, which you can see over on the right. An RNN can actually feed information back into itself, which gives it a kind of memory. But our FNN? Nope. It has no memory of what came before. Every single piece of data is a completely fresh start. This makes it super simple and incredibly fast. But that lack of memory also leads to some really interesting limits we're going to talk about later. Okay, our little data packet is officially at the front door of the network, ready to start its trip. Let's see what happens right at the beginning.
This is the starting line. The input layer is where you feed the network all the raw information, just the basic facts. So if you're trying to predict, say, a house price, this would be things like the square footage, number of bedrooms, you get the idea. Or if you're trying to spot a cat in a photo, it's just the raw color values for every pixel. This is the raw material the network gets to work with.
So once that data gets inside, it starts getting processed by layers of these things called artificial neurons. But what is actually going on inside the mind of just one of them? Let's zoom in and take a look. It's really just a simple two-step dance that happens over and over. First, the neuron looks at all the signals coming in from the layer before it. It then multiplies each of those signals by a weight, which is just a number that represents how important that signal is, and then it adds them all up. That's the weighted sum. Then step 2, it makes a decision. Is this combined signal important enough to pass along? And that decision, that's made by something called an activation function. Let's make this super concrete, okay? Imagine our neuron gets two inputs, a 0.6 and a 0.2. It decides the first input is pretty important, so it gives it a weight of 1.5. And it thinks the second one is kind of negatively important, so it gets a weight of negative 0.7. It just multiplies them, adds a tiny baseline number we call a bias, and boom, it calculates a final sum of 0.86. It's really just simple multiplication and addition, but happening thousands, even millions of times. Okay, but hold on. This brings up a really good question. If the neuron just calculated that number, 0.86, why not just pass that number straight to the next layer? Why do we even need that second activation step at all? Well, because without it, the whole network, no matter how many layers it has, would just be doing really simple straight-line math. It would be like trying to draw a complex picture using only a straight ruler. It just can't learn curves or corners or any of the messy, complex relationships that actually define the real world. That activation function, it adds the ability to learn complexity. It's the secret ingredient that gives the entire network its power to learn. All right, our data has been weighed, summed, and activated all the way through the hidden layers. It's finally reached the end of the line. So what now? Well, now it's time to get an actual answer. And this is cool. The final layer is custom built for the exact job you want it to do. So for a simple yes or no question, like, is this a cat photo? It uses something called a sigmoid function to spit out a single probability between 0 and 1. If it has to choose between a bunch of options, like figuring out which number from 0 to 9 was handwritten, it uses softmax to give a probability for each category, all adding up to 100%. And if you just wanted to predict a number, like a stock price, it can just output the value directly. It's all about picking the right tool for the job. So we've seen the whole journey, from start to finish. We get how an FNN works now, but is it any good? How well does it actually perform? Let's give it a little report card. check out its strengths and its weaknesses.
So on the plus side, FNNs are simple, and that makes them really fast and pretty easy to train. They are absolutely fantastic for working with structured data. Think of anything you could neatly organize in a spreadsheet. And here's the wild part. Theoretically, if you make an FNN big enough, it can learn to approximate almost any pattern in data. They are a super powerful and reliable place to start.
But, and this is a big but, they're not perfect for everything. Remember how they have no memory? Well, because they look at every input on its own, they have no built-in idea of sequence or order. That means they're not great with things like language or financial time series data. They also don't really get spatial relationships, which is why more specialized networks are almost always better for things like image recognition.
And if you ever find yourself building one of these, there are a few classic mistakes you've got to watch out for. The number one is called overfitting. That's where the network basically just memorizes the data you showed it instead of learning the general patterns. It's also really important that all your input numbers are on a similar scale. And like we just saw, you have to make sure you match that output layer to the specific problem you're trying to solve.
So there we have it. We've traced the entire journey. We've seen that at its very core, this AI brain is just a simple, one-way path where information gets processed through tiny decisions at every step. Which leaves us with a really fascinating final thought. If this is what the simplest AI brain can do, what kind of mind-blowing problems can we solve when we start stacking these layers not just a few times, but hundreds or even thousands of times deep? Now that's where the real magic of AI begins. Thanks for joining me on this one.